So, um, so if you do this probability prediction problem, and then we look at a very simple case when you have binary. So in the case where you have just the binary of the y to predict, that's the classification problem. And we also looked at the very simple case where you have x's in some discrete feature space. So the x is also binary, for example. And spent a couple of lectures talking about this situation and how to find the optimal classifier, which is a function from x to y, basically. Or let's say this is the space of y. This is the space of x, right? So you want a function that goes from the space of x to the space of y and predicts the y based on x. So we introduce how we measure the performance, which is via a loss function. So you introduce a loss function, which measures how well you predict. So this function of x is going to be y hat. So we introduce the loss function and measure how well we predict y by measuring this loss space. Okay, so there are different, many different loss functions in general, but we consider the specific one we'll talk about. But then you have a risk which is associated with your classifier, which is going to be the expectation of this loss. Okay, and so the specific loss function was if you have the 0, 1 loss, you would have L of y, and y hat is just indicator of y not equal y hat, in which case the expectation would be the probability of y not equal y hat. So under the 0, 1 loss, the measure of performance is measuring how often you misclassify, or the probability of misclassification. So you get P of y equal f of x. I'm going to go over the details right here. But then the question is like, what is the optimal classifier at this point? And we break up this. So this is called the risk. We broke this up by conditioning an x, and then write the optimal rule, which in this case would be not some rule that you could take it. But then this is all under the assumption that I know the joint distribution of the xy pair. So the assumption is that x and y are coming from a joint distribution, which if I know, I can compute this optimal rule or the Bayes rule. Well, we don't know it, so we try to estimate this probability by average this from the training data, and then this leads to this plug in optimal rule. And then we discuss different types of error, which include the test error, the training error, generalization error, which is the same as the test error, and the validation error is very similar to the test error, but for some reason we separated from training. And then you talk a little bit about model computation. So this was the structure of chapter 1. And so the main idea is you start from this problem, the predicted problem, reduce to classification where y is 0, 1. And you further reduce to where x is discrete. And you saw that this is, it's not a problem if you have like two discrete features. Basically, you would have combinations. So you had like this P class, which was, so you had like sex and class, which gives you all these combinations of sex and class. So you have like discrete feature with 6, for example. So basically, all the things that we discussed for binary feature extends to categorical, more than one categorical feature once you consider all combinations, the same way you apply. So in this simple case, so a bit more generally, we discussed how to measure performance, how to find the optimal rule if we know the joint distribution. And in this simple case, we managed to actually get an like estimation of the probability using averages and an estimation of the optimal rule. So let me like remind you what the setting was. So so the oracle problem is where you assume that you know the joint distribution, etc. So we discussed what happens, what the optimal rule is in this oracle situation. Okay, so there was a majority rule classifier which I skipped, which just predicts based on just y, with knowing the classical portions of y, ignoring x. So you should know about this majority rule classifier. We added one feature and binary feature. We introduced this risk based on a loss function, which could be 0, 1. And what we did is, if you go through this part, so we sort of did this condition. I think what we first did is propose. Earlier, I think we proposed that we should classify based on the conditional probability of y given x without any justification, and then we calculated the risk by conditioning by x, and then we realized that okay, if I do this conditioning by x, then I can actually figure out the optimal rule. I don't have to guess. So what happens is when you condition on x, there is this piece which so there's this piece which I can't control, and then there's this piece which I can control. Okay, so this piece that I can control is the probability, for example, that y is not equal to a particular decision given x. So if x is, for example, female, I can try to control this. Because, sorry, we have to do it the other way. Let's go down. Yeah, so I'm going to write the risk like this. Now, I don't know f, and what I do is I do conditioning on x, and now if I have x chicks, here I'm deciding as a female, and so I can minimize this probability. Okay. Choose the decision f of f that minimizes this probability. So your choice is either 0 or 1 here for f of f. And you plug both in, and you get two probabilities, and you find the one that is. The same goes for this guy. So you're gonna choose f of m, for example, equal 0, 1, and then if like once, and then equal 1 once, and this gives you two different probabilities here, and you choose the decision which one of them based on which probability is small. Okay, so when you do this reasoning, you arrive at this that the rule is the same, and they're both like female and male, and every time you minimize, you find the decision that minimizes this conditional probability, and that's what gives you this optimal rule. Okay, argument probably that y is not equal to b given x. Okay, so that's the base classifier. And if you go a little bit further, you realize that the same argument applies not for the 0 loss, but for the general loss, and not only for discrete x, but for general x. So you would get this very general, the composition of the risk based on this is the marginal distribution of x, and then the minimizer would be somewhere down here. So that's the general optimal rule. So I give it a side second side, but you can try to do it for yourself just from let's say from this decomposition. From this decomposition of the risk by conditioning on x, you realize that you need to minimize this. So in general, if you have the expectation of loss of y and f of x, this is the most general case, this would have the decomposition expectation of loss of y and f of x conditional on x equal x, and then this d nu x is, you can think of it as just px dx if you want. First, this is the marginal density of x. Okay, so this part I can't control. This one I can minimize. So you find from this, it follows that the optimal rule is argmin. I can control this. So argmin expectation L, Y, and D. I put a D here, condition on X, and then D is on, let's say in this case would be on the space of Y. So whatever Y takes. So this was my relation in the range of Y. So that would be the expected optimal rule. If you plug in the 0, 1 loss, this would give you back this rule. Okay. In the case of classification, and here is a good point that later we came back to this and replaced this loss with quadratic loss. Okay, and then in the context of regression, so in regression, L of y and f of x would be y minus f of x squared. So the optimal rule from the above would be argmin. In this case, D would be in reals, let's say, because that's the space of y, and then the expectation of y minus D squared condition on x. And hopefully you guys remember what this was. What he said. Yeah, so this would be the expectation of conditional expectation of y given x, which is what we call the regression function. Okay. So in the context of regression, it would be the regression function. In the 0, 1 last case, which is, I mean, here it would be, you remember what so this is going to be Zeka 0, 1 function, rather than real value. So if you do the sort of math, it would be equivalent to doing this eta x bigger than 1/2. Eta x less than 1/2, where eta x is again the regression function in this case, the same regression function, but in this case it would be the same as the probability of y equal 1 given x is equal to x. Hopefully you remember because y is binary in this case. So this regression function is pretty predominantly in this discussion. In the case of that's a binary classification, your threshold is 1/2, let's say for 0, 1 loss. In the case of regressions, this is just the solution of this regression. Okay, so that's sort of the general picture. Okay, risk minimization, the big picture. Okay, so that's sort of everything that you need to know at the population level. If you knew the distribution, these are the optimal things to do. The problem is you don't know this joint distribution. So we assume that we have a training data with the I8 example, and then we try to estimate. Most of our time we spend estimating this conditional expectation. Yeah.
So I think this was a problem for the homework that we recently did to show that for the y minus that squared.
Yes.
That you end up getting the regression function.
Yes.
Is the way to do that multiply out the y minus d squared term? And like what's this? When you say it, it sounds very good. You condition on x and you get the answer. But like written out, what are the lines to that solution?
Right. So from this to this, right? So what do you guys think? How do you?
You expand it and you take the derivative.
You expand it, you get a quadratic. So you'd get like expectation of y minus maybe we do it like separate page here. So I want to minimize this as a function. Let's call this, I don't know, g of d. So it's a function of d, y minus d squared, conditional on x. So the natural thing is to expand, right? So you expand, you get the expectation of y squared minus 2yd plus d squared, given x is equal to x, right? So then what? We set the property with expectation.
You know, it's been a small bit to begin expectation of X plus.
Expectation of the sum is the sum of expectations and also scalar multiplications come out. So this is linearity of expectation. So if I have expectation of alpha, let's say x plus beta y, I get alpha expectation of x plus beta expectation of y. Right? So it's called linearity of expectation, one of the important properties. Linearity of expectation. Assuming that alpha and beta are deterministic. And this conditional expectation is the form of expectation, so it has the same property. So I get expectation of y squared given x. Minus 2d again is constant expectation of y given x. Plus d squared is constant. So what is that? Okay, that's linear expectation. So what is the next step?
Derives with respect to D.
Sorry?
Derives with respect to D.
You take derivatives. Yeah, so this is like a function of d. I just find this calculus. It's a linear numbers. So I have a function of d, which is actually a quadratic function. You either know it by heart for the minimum. Sorry, it's like a quadratic function with the coefficient being positive, so it has a minimum, it's the length. Or if you don't remember, just take the derivative, you know that like this gives you the limit. So this looks something like this. Okay. So a quadratic function where the coefficient of the highest degree is positive is convex. If it's negative, it's the other way around. So it has, in that case, it's maximum. It has a maximum here, it has a minimum. So I'm going to take the derivative d2. Yeah, that's bad notation. So let's say partial with respect to d, okay, of this quantity, say it equal to 0. So if you take the derivative, what happens? This is constant, goes away, right? So this is linear. I get -2 expectation of y given x plus 2d equals 0. You solve, you get d as expectation of y given x. Okay. So if you do the same without conditioning, what do you think you get? The expectation of y. So that would say that the best like constant prediction of y is the expectation of y in the MSE sense. The best like conditional expectation, the best conditional. So this is saying if I know x, what is the best approximation of y, and it turns out to be the conditional expectation. It's good to remember. At the end of the day, we have proven that actually, like the best predictor of x given. So once you plug in this, so what this the content of it is saying is that if I minimize, so argmin expectation of y minus f of x over all possible functions. So the best function of x that approximates y in the MSE sense is the regression function. So that's what we proved. The argument is expectation of y given x. How did we prove this? In 2 steps. First, we proved that the solution of this is of this form. This comes from the general consideration of this conditional idea. So this has a structure, and then this, in particular in this case, this would be that. So we proved that the best MSE approximation. Okay, so I have y, like I don't see y, I see x. I want to predict y based on x. The best function. This is the definition of the best approximation. Best approximation in the MSE sense, the quadratic law sense, is the regression function. Okay. Everyone happy with that? Okay, so there's things in this chapter that are more general. So it's a little bit hard to Okay, then, so we started with the discrete case, but then this part is very general, applies to later. And then we came back again to, because the general case, you can figure out that an approximation of this is harder than X is continuous versus when X is discrete. So we came back to the discrete case for approximation. So again, I mean, this is, these all should be familiar at this point. So we go back to this optimal rule for a while. Oh, maybe before mentioning that, there are a couple of exercises here that go through sort of models that have a particular conditional model of X given Y, or Y given X, and X. So, for example, this exercise is giving you implicitly what the joint distribution of Y of X is. Once I specify the conditional distribution of Y, sorry, the marginal distribution of Y and the conditional of X given Y, I've given you the joint distribution, so you can, for example, calculate this optimal rule. You have to compute this regression function, which you can do by Bayes' rule, and things come out. The same goes, for example, for these problems. And, both of these problems, there's different ways of specifying the distribution of X and Y, which we call past conditionals, and the same principle in this case applies. So I specify given Y and also the marginal distribution of Y. You can invert this relation with Bayes' rule. You get the condition like probability of Y equal 1 or 0 given X, which probably Y equal 1 given X is enough in this case, and that will give you the regression function. In this case, you have to compare it with 1/2. That's true. That we did the general case here. You can see, like, if you have, this is the structure of the optimal rule. When I give you a density, for example, in this example, this is a general density. This is done more general. So we compare the likelihood ratios to the threshold. Here the class conditional densities. We compare it to a threshold, which is related to those marginal probability of the Y. So marginal probability of Y equals 0 and 1. And the same, this would be 1 to compare this to 1, otherwise you compare to 1. So this is like a likelihood ratio, calling it likelihood ratio classifier. This is a very specific application of those ideas in this setting where you get the class conditional density. And so this example, if you go through it, these two problems are basically just examples of that. And this particular one is a classical approach. Classification we assume the class of the red Gaussian. With mean, which is different than sigma, which is not. And if you find the structure of the optimal rule, it would be the linear function compared to C. So this is like a hybrid thing. So you classify to one side of the hybrid thing. And this is called the linear discriminant analysis of Fisher because of the decision boundary in the linear. And later, if you don't know the sigma and mu, you actually estimate them from data because you have a parametric model. In this case, it's easy to extend to when you don't know the joint distributions. You could assume the parametric model. You only need to estimate the parameters and you can do it. So you go to class 1 training data, you take the average, you get the mean. So you get mu for example 1 and mu 0, the estimates of them. And you also get the estimate that the covariance can pull all the data together and you can get an estimate of the covariance matrix you plug in X here. And so this W and C, if you have done it, you can say W is here, C you can figure out. So based on sigma and mu, so you get halves of these. So you can implement this in practice. So this parametric models are easy to sort of do, once again, it reduces to an estimation of the parameters, which you can subject to separately, plug in. So it would be the plug-in of the Okay, so this discussion was also like an offshoot of optimal classified, optimal. So questions? Okay, so then we went back to classification. Okay, so one more point before. So we also talked about this cost sensitive learning, which is um, worth remembering. So this is once you understand what is going on with the, we actually didn't talk about it much, but you did it in an exercise. So once you understand this general framework, so any loss that I give you, you can optimize it. You can find the optimal rule by this formula, which is, you can think of it as the minimizer of the cost theory risk. So if the loss was 0, 1, it would be symmetric. So the way that penalizes the error is symmetric, whether you have y here equal 1, and you specify it as 0, or you have a 0 specified with 1, you pay the same price as 1. So the loss is symmetric, but you can have a different loss. For example, in general, the loss has like 4 possible choices. So L00, L01, L10, L11, let's say, or I should better write it like this. I have L00, L01, L10, L11. So if you specify the square, you specify the loss in the binary classification because y and y hat are, so this is like Ly, y hat. Okay, so let's say this is y hat. I have to specify 4 numbers in the 0, 1 loss. This is specified like this, 0, 0, 1, 1. So you can see it's symmetric for the 2 errors, but it can be asymmetric. For example, I can have an asymmetric loss, or I can have like 4 different numbers, like 1, 2, 5, 6. I can penalize being correct. So like prevents it. So you can find what the optimal rule would be. If you don't want to be correct, let's say I want to be like it's very bad if I'm like doing good. I don't know if you can find an example of that. But oftentimes these are 0, right? So being correct usually has no cost. But it could be that these 2 numbers are different. Based on that, you go through this calculation and you find out that the optimal rule again looks like something like that, but this 1/2 is not going to be 1/2 anymore. So if you go through the details of this exercise, you get that the optimal rule is still structured. It's like comparing the regression point of the threshold, but that threshold depends on the way you specify the loss. And so it's sort of give you what the optimal rule is in this cost sensitive thing. Sometimes called cost sensitive learning. The other learning all themselves. But once you understand the general idea, this is just a special case. Okay. Everyone happy with this? So this was like one of the questions that people asked. I hope people know how to do this. Okay, this power would depend on L0. So in this case, L0, 1, and 1, 0 are general. And so this would depend on these 2 numbers. If I give you like 2 and 5, and this is the number, I think no, it comes out of the function of these 2. There is some connection to pass and balance. So some people use this to handle pass and balance, but let's not worry about that for now. Okay, so far so good. So that's what all about like optimal rule when you know the joint distribution. Then we came back to the case where we don't know in the discrete case. So in general, we get a training sample from your true distribution, and then the idea was to approximate or form approximation of the joint distribution, which I can do in the discrete case by this formula 14. This is just averages. Okay, so you look at all the possible combinations of y and x and count how many you observe in the data divided by the total number, and that's proportions of those, and that will be an estimate of the joint probability distribution, which is like a matrix in really discrete. And you can use a valid probability distribution. It follows all the rules, so you can do like, for example, conditional distribution, which is like the joint distribution, which is that, divided by the marginal distribution, which is this. You also marginalize this, or this is marginal distribution takes with the portion of learning the features at a big level in the data. And so this bit must be approximation of the regression factor, the conditional probability y to x. And so I can write down the plug-in, well, what they call plug-in optimal rule. It's not standard, but this approach is called plug-in because you plug in into some estimator that you know. So I needed this regression function. I plugged in my computer constant. So that's eta hat here is just this, right? Or if you want eta hat x is again probability hat of y equal 1 given x is equal to x, which turns out to be the probability I from 1 to n, indicator yi equal 1 and xi equal x, divided by the same thing, I from 1 to an indicator xi equal x. But yi equal 1 is the same as just yi. So if yi is like either 0 or 1. So this indicator of yi equal 1 is really yi. Okay. Think of it when yi is in 0, 1. So this has this alternative form that I can write as yi times the indicator of xi, and then divided by the indicator of xi equal to x. And this further has the structure of summation I from 1 to n, wi x yi, where this is wi x. Okay, so it's like a weighted weight. So the weight that you associate with I training x based on your current. So you have like a test x, like little x, you want to predict. You want to do the prediction for this particular x. This is how you make the training one for that particular x. And this simple idea is extendable. Okay, so when I don't have, so if you have this, you plug it in here, you convert it 1 after the plus. And this idea is extendable to the case where the xi's are not discrete. If you look at this carefully, you realize that perhaps this is a form of similarity. So we're measuring how close xi is to x by saying if they're the same, they're perfectly similar. If they're not, they're just perfectly dissimilar. But I can relax this assumption. Instead of the indicator, I could have something like a kernel here, right? Xi. I forgot how it works. I think probably write it like this: xix. So that indicator, if I replace with the kernel, these are sometimes called kernels. So indicator of y x. So xi equals x with the kernel, but the similarity of xi to x. Okay. So this similarity is like I'm writing it very generally because it could be very general. But generally, if x is similar to xi, which is high, if x is this similar, this is low. So this acts like a relaxed version of the image. So once we realize that we can do this, then this generalizes to discrete features, multi-dimensional features, and so on. Because I just need to define the best part. We call these local averaging because so this is local averaging. Because okay, so sometimes this similarity is based on distance. So let's say if I define, for example, okay, so let me go down here. So this is like chapter 2, basically. So one way of defining the similarity is via this notion of a translation invariant kernel, or like not translation invariant, but this is one special case where I have a base kernel and then I apply to xi minus x divided by h. In the case of the Gaussian, it would be like the Gaussian kernel, it would be something like that. Either 2h squared or h squared. So if my base kernel is e to the negative u squared over 2, I get something like that. And you can see this kernel. So if little x is close to xi, is exactly equal to xi, this is going to be a 0 and it's going to be 1. If they're very far apart, this norm is going to be big. And so this is going to be very small. Okay. So if you plug in this kernel there, you can call this local averaging because it's gonna average yi's that are close to little x, and it's actually averaging over everything, but it puts weights on the things that are closer to x. So if I have x here, the contours of this function would look like, so they go down like that. So it's very large here. So I can visualize it like this. So imagine like a mountain. So the peak is here at the x, and it goes down as you move away. Okay. So these are the contours of this function. And so if the data point is here, it gets a smaller weight because the x. So the x is here. So this is the x domain. So this is xi, for example. This might be xj. So this xj gets a very large weight. This xi gets a very small weight. So you average the corresponding y's according to how far you are from x. And so you can think of it as things that are local closer to this gets more weight. Like if the kernel sort of is the box kernel just pops off. So for example, my kernel is so the Gaussian kernel, it could be indicator, right? It could be 1 if xi minus x squared divided by, let's say, h squared is less than 1, 0 otherwise. And so this one you can write it as so box kernel. So it would be indicator basically xi minus x divided by h less than or equal to 1. Okay, which is similar to saying that it's going to be 1 or 0 depending on whether. So whether xi is close to x. So if xi is close to x, like closer than h, then you put a price like you say the perfect is. If not, it's going to be 0. So there's a box of length. Okay, this is actually not a box. So this is going to be actually a circle. So it would be box if this is L infinity. Okay, if it's L infinity, it would look like infinity norm. Okay, check out the infinity norm is the maximum absolute value. But if this is the infinity norm, this would look like a box. If it's a true norm, which is essentially, perhaps we shouldn't call it, it would be box kernel in 1 dimensions, because in 1 dimensions it would be interval. But here it would be actually like a circle, because the L2 norm. So this is a circle centered, or like a spherical thing centered at x with radius h. So any xi that lies here gets a weight of 1. Anything that's outside get a weight of 0. Okay. So this is a sharp transition. This is like slowly downwards. This is like sharply downwards. But it's the same thing. So this is what I call box trend path. We should call it box. It would be the same same like in 1 dimension. It would be just an interval. So you get an interval of side length. Maybe 2h, the x plus h, x minus h. Now, if you change the norm, there are different norms. I can change this norm. This is L2 norm, I change it to infinity norm, for example. In higher dimension, it could change it to be different. If I change it to L1 norm, it would be a diagonal. Would be circle, diagonal, and like box. So. Okay, so that's the idea of local averaging. And so this particular version where we do this, and we have a banded parameter, this is called the variable Watson. But this more general form, for example, includes things like nearest k nearest neighbor. So the similarity could be x is similar to xi if xi between the k's nearest neighbors, the little x in the training data. You look at the training data, you sort the xi according to the distance to x, And the data points that are within the K nearest get weight 1, the rest get weight 0. So if you think about this, this is going to be always K, and this, the top will also be a sum of the K pairs. So you're averaging over K of the Y variables. But that doesn't look like this Landau-Johansson business. It's not translation. So not translating, right? It's not translation like this. So this is obtained by translation of a single kernel. That's not like that. But the same sort of principle that it works. And so we started analyzing like something like this. And we analyze something which is even simpler, and it also lies in the class, but it's not in Landau-Johansson, which shows the partitioning. Yeah.
Yeah, I did for the box kernel, so like if we use the box kernel, is it possible to get denominator as 0?
It is possible, yeah.
That way, like, what do you need to do for?
So what do you guys think? What should we use?
A very, very small number, and the denominator is 0, then the denominator equals.
Yeah, you could put it like a little number here to avoid the division by 0, but that's maybe like an active way of doing it. The issue is that if you have a box kernel, what will happen is, let's say, I have my data points, and you're predicting at a point where this like circle does not contain any other thing. So I would say call it undefined. So that estimator would be undefined for this. Okay, and so you have to deal with it somehow, but this bandwidth is too small, let's say. Okay, maybe you can increase your bandwidth. And hopefully within the range of the x's that you consider, at least one of the data points is inside. So in the bandwidth selection process, you can sort of rule out those cases because that would be like a better choice. So I'm gonna at least make it big enough so that hopefully for the range of x's that the customer, let's say I want to predict in this box, for all the x's in this box, when I vary the circle around, it will capture one of them. So that's what I would do. You can also leave it undefined, do something else, but that's like a deficiency of this. So that doesn't happen, for example, for the Gaussian kernel, right? Because the Gaussian kernel is positive, you still get like everything gets a weight of very small. So, but yeah, in practice, you have to like worry about it.
Well, if the edge is too small, the computer doesn't compute the ones that are too far, the points that are too far from your X, even though you're using a Gaussian kernel. You know,
So again, this is going to be weird.
yeah,
Yeah, so let's say in R, maybe, yeah, you're right. If that's very large, then just up to 0. True. So there's like issues with numerical precision. But in theory, this is like in math, this is never 0. In practice, this would be 0. Okay. So you have to deal with that. Okay, so that's the general idea, right? The partitioning estimator is similar, but it does what it does is just it partitions, right? Let's say I partition the space. And so you would see how many data points or which data points lie within a particular cell, and you also determine your little x is in one cell. So the cell of the partition that contains x we call, so these are like A1, for example, A2, these are different cells, okay, A3 and so on. The cell of the partition that contains x we call this AX for analysis, right? And so this partitioning estimator is the same as this local averaging idea here, with this kernel being, so it would be similar to this, or like within that general class. You can call it similarity averaging if you want, where x, k, x, and x is just indicator of x in, sorry, xi is in x. One if xi is in ax. zero otherwise. Okay. And we analyze this particular estimator, we did the bias variance decomposition, which if we have time, talked about. But depending on what so my plan is maybe to go through the code at this point. I also saw the code, some people had difficulty implementing these. And it might be instructive to go, it's Python code when, in the age of ChatGPT, you can figure it out hopefully. Plug it into ChatGPT, let it explain. But it's also partially developed by ChatGPT, so we should know. So, let me go to the code, that sounds good. And then maybe we can, if I have time. So let me show you how one way of implementing these ideas. It's good practice to like, so this is not perfect software engineering, but you can like collect functions or like things that are you're going to use later. So you put things in little functions or classes and then collect them in files that you use with modules in Python. And then you call them. So I have this helper .helpers.py contains some of the things that are useful. So for example, this plot contours, plot the contours. There's this plot decision level sets that we talked about. So you need a model, PyTorch model, which essentially is a function and evaluates it. But it's assuming all of this assumes that like things are three-dimensional. There are two features because otherwise we can't. So this contains a bunch of those, and the models. This file contains the models, and you need not. So this is like a little bit over engineered, let's say. But I wanted to introduce this because it's useful for future PyTorch kind of development. So this is, for example, my version of implementing the Nadaria loss. Okay. So what is this? This is how people in PyTorch implement models. So you do the import torch NN. So NN is as NN. So now I have this NN module basically, or like NN the Python module, and then there's this NN dot module, which is like the base class for these models. So this is a class which I define myself, like another one, say call it in E1. The convention is usually starts the class names start with uppercase. So it would be like Nadaria, but okay, it's just up to you. So this is a class. And this is going to implement a version. So when I instantiate this class, I get an object which is another once model. Okay. For example, my idea is that I'm going to apply it to this data set that will be the very once object. Apply it to that data set, it's going to be a different object, but they have the same functionality. So this is like encapsulating that functionality. So the first thing is, so it inherits from this NN module, which has a lot of interesting functionality. So all those functionalities are going to be there. When we need it, in this particular case, we don't need it because it's exactly against convention. This is the construct of the class, so it initializes everything. And if you haven't seen Python, you pass this, the first argument usually called self, you pass it through this, and when you instantiate, this is going to contain the object. Okay, so for example, in this constructor, I set some fields or like properties or self that exchange is going to be exchanged. So when I instantiate this model, I get an object that contains the training data in this field, contains the Y training data in this field, and a lot of like software things that you have to worry about. So this is ChatGPT sort of ensuring that the type of the Y train is the same as the type of X train, so one is not like float 32, the other is float 64, and then random feature. So there are these things that hopefully in the age of ChatGPT can figure it out. And then I also like have a kernel, which is this is going to be a function, so you can pass functions along with Python also in R. So default is this Gaussian kernel, which I defined here. And so if you want to change the kernel, you pass it to your own function, you pass it here, and you will be not relatively packaging. Okay, so the way I sort of like wrote it, there are many different ways, but I define this these kernels between an x and x string. Okay, so what it does is so you give it like a matrix X and it's changed. So this could be like m rows, but this side is e features, and then you have n, and again e features. And what it gives you is like this m by n matrix. Okay, it contains kx, let's say, and I should write that xi, let's say little xi and big xi if you want. So little xi is the ith row of this. Maybe this is too confusing, but that's it. Right, yeah. But hopefully the distinctions can you choose field differently. But this is like capital Xi is the ith row of this. Little xi is the ith row of that. So this is the ith row. This is the j row here. So this gives me that. We let me do it differently. So let's say this is I know zi. So that you not confused, this is zi. So the ith row, the j row, these are d-dimensional data. There's a kernel value for that. So this gives me that. So this gives me a kernel matrix which is m by n. Okay. And it like measures the similarity of the ith row. So this is for us is going to be as I'm calling it capital X. This is X string. Okay, or you can call it X test if you want. Yes.
So it's a row to row comparison?
It compares every row of this to every row of this. So there are m rows here, n rows like m times n pairs. All like possible comparisons of.
Oh, I see, and
So this gives you an m by n matrix.
what in the code gives you that?
So the way I want these function kernels is doing that. So X is the first matrix, this is the second matrix, and this is going to return that matrix. So this C distance or C distance computes the pairwise distance. So if you do X and X train, this torch. See this. This gives you pairwise distances. So it gives you a matrix. The ij element is basically zi minus xi.
So that Gaussian kernel function returns a whole matrix.
The whole matrix, yes.
Are you saying that, so you will have like, a similarity for each test point?
For each test point, so this would be, let's say, one test point. Right, you have n, similarities with n of your training data, so you have n numbers. Right?
Oh.
So and that would be like the ith row of this. Right, how similar this test point is to all the n's. And how similar another test point is to all the n's is the other row, right? So you need this. So if you just testing at what point, let's say in our discussion, we usually have just a single x. You can just pass like a single x. Right, I can do this kernel. For a single x, it would just be just a row matrix. So this k x xi, if I collect them into a vector I from 1 to n, I get that. So this you can do also in the code. You can just pass it. We'll say later on you can pass any number of rows, but the convention is often that you want to calculate the multiple test points. So usually your test is like multiple, and so you want to write your functions or models such that they can operate on multiple samples at a time. Okay, and this is useful in this case because this operation is fast, so you don't have to do full for loop. Some of the technology that in this code, and also in R, you can vectorize it. So this vectorizes. So it's code that is written in C, for example, so you don't have to do the for loop. So this just computes the pairwise distances of all the rows of this and all the rows of that, and gives you that. Then my Gaussian kernel will just take this and do something like minus this matrix squared pointwise, which is there. And then divided by, and here I have to divide by h squared, which is a python like this. And then one range. I can leave it here or drop it. In this case, because of the divisions, it doesn't matter. But yeah, I put it here because for some reason it's good. If I want to later add like construct kernels from Samza, Gaussian kernel or something else, this might be useful. But if you just do it in another area, and this actually has not. So that's the Gaussian kernel. Also, if you want to, I will show you another example. If you have your own custom kernel, you have to, if you want to do this, use this logic, you write something that gives you the pairwise similarities, whatever they are. It's a partitioning or like k-nearest neighbor, you can find it like that, or something else. So once you have it, this is actually like more general than going lots at this point. So they have value. So okay, so this is how you visualize. And then there are these classes always have a forward method that you overload, you redefine it your own way. So they're expected to have a forward method. So these are the, so you have the visualization, which is the constructor, and I have a forward method. What it does is that when I call the, like, when I apply the model to data, this is going to get called. Okay, so this is where the action happens. So, what happens, for example, when I sort of create a model of area one something, I give it the initialization, for example, I give it like X train, X Y train, and a kernel is a Gaussian kernel. So now this is an object. So when I apply this object, so this is going to be the solve in after initialization. Whenever so this code gets run, self refers to this model. So when I apply it, for example, to X and give it X, for example, 3.0, this is going to call this function. So this is equivalent to saying like forward model X E. Okay, so this just translates to that. Okay, so the variable is something like that. I'm not quite on expert, but this is equivalent to saying the variable in class forward. Take this method of the class, apply it with the model X entry. So this is like you apply these models like functions. Okay, so it's an object, but it acts like a function. I can drop this. I can usually just apply it to X, but I can pass it any number of parameters that I want. It takes X and a bandwidth and turn X into the same type as the X string. Compute this kernel, which is these X, so that's the m by n matrix, this matrix, right? The kernel matrix. And then this is the implementation of the variable. So why is that the implementation? Because so if you imagine, I'm trying to calculate the f of, let's say, the I for all the i's, okay? And this is going to be 1 over, you'll actually be 1 over n, so it's like summation k to the I k to j, and then it's going to be y j from 1 to n divided by summation from 1 to n k to the j. Yeah, that's that. So if you look at this, this you can think of it as a matrix multiplication, right? So this is so the ith row of that kernel matrix, which is k zi dot, I'm going to put dot here. So I have x j variety. This is going to be 1 row, and then I multiply it by so this vector y, which is this is like y train. Okay, but the elements are yj. Y1 to Y2. Okay, so each row of this multiplied with that produces this. Okay, so now I have multiple rows. If I do matrix multiplication, each row gets multiplied. Okay, so when I do this matrix multiplication, this is matrix multiplication. Weights, that's the kernel matrix multiplied by self y train. That would produce these for all the zi's. So it gives me a vector n by 1. So this is n by n. This is n by 1. So the result is n by 1, which is the numerator. And if I multiply by the vector of all ones, it gives me the denominator. Okay, it just sums every row. So that's the second. So for ones like that is like creates a vector of ones that the same shape as Y train. So first I multiply by Y train and then also multiply by a vector of ones of the shape Y train. And then divide, that's a like pointwise division. So this acts as matrix multiplication. Well, everything else is like pointwise. So let's just implement like in one line that local averaging. Yes.
So the numerator and denominator matrices are both like columns of
At this point, they're columns.
number of rows equal to X that you feed all. Like,
Yes. So you take, like, technically, they're not column vectors, they're
They're
just
not-
vectors. Yeah, so
They're
like, yeah, so they're like mathematically they're column vectors, but in PyTorch, there's a difference between like a column vector. The column vector has shape m and 1, the vector has shape m and nothing. Like it's just a minor distinction.
Okay.
So this is like two-dimensional, this is one-dimensional. But you can pass between them, yeah.
And so you define your model, you call NW, and then when you're using your model, you feed it like the test or validation data. You don't have to actually pass it the training anymore, right?
Right, so so this is one design, it could be different design, but the way I designed it, at least this version, I passed like X trains, Y train, and the kernel once, so now I instantiated the model. Now this is the Nadarya-Watson with these things, so I can now apply to different data, right? And I sort of designed it again, and so in a previous version, the bandit was also here, so the bandit was baked into the model. Now I'm just passing it in the forward path because this would simplify when I want to select the bandit, right? So I don't have to re-initialize this. So let's say training data, if this is big, this is done once. And then, for example, I want to apply the model with different bandwidth, I can pass it. Sounds good. So if you like play with this a little bit, you can do it like with for loops and everything. Like this is not necessarily not claiming this is the best way, but this is pretty hopefully fast. And it's like a sort of maybe misuse of PyTorch because PyTorch is like designed to do like training. We'll talk about that, but it's good to write it this way because now you can compare it with like neural networks. So there's zero training going on here. Like it's just initialization application. The minor training is in Edge and then we do it separately. So let me maybe show you one example. So this is used in both this solution, which is a little bit more tricky. I'm not sure if we have time. This defines a costing. Maybe let me tell you about this first. And this is the breast cancer data. And then there's, okay, in these loaders, there's this load breast cancer, which you can go, it just does a lot of cleanup, like loads the data, cleans it up so that we are in starting position for, yes, if I run this, for example, let's see if it runs. Let's do. Okay, it ran and you can see like X train, for example, is a torch tensor, and you can see the shape that's like 398. And then there's the X test, which is 171. So that's like M.
And you wrote a function to load in the data in some other
Yes.
file.
Yes, so the other file is this. So with loaders, and it's there. So from loaders, import this. Okay, so now I can use this function. And if you go this is the loaders, right? It loads like this data, which is like there are a lot of messy things to deal with. Like you load it as a pandas or a data frame, like in R, but then you translate. I'm doing a bit of things here, so I'm dropping DNAs, which may or may not be a good idea. But hopefully like you can figure that out. So that's the thing. So that I have the X test and then the train. So here, for example, I'm calculating that you can see the kernel matrix applied to X test and X train, and the bandwidth is 3. And if I run this and then print the shape, you can see it's the shape is 171 times 390. So using that n by n matrix, and you can plot it. There's also like a nice like plot here. This is in if you go through. Right click. This is in the helpers, as you can read. Like this is ChatGPT's suggestion how to get like a working, nice colorful and stuff. But this is sort of plot that kernel makes. It gives you yeah, it gives you. You can see this the similarities. If I change the bandwidth. If I make it smaller, to the one of zeros, okay, if I make it larger, if I make it very small, you can see what happens. Okay, 0. So very small, everything is close to 0. So there are very like few things that are similar. If I make it large, you can see like a lot of things are not similar. Everything is basically similar. So this bandwidth measured how similar, and if you think about how the Gaussian kernel is working, that makes sense. Okay. So play with this, and then here's when we apply it. So I take a bunch of edge values, and then I initialize the model. So you can see the model is Nadarya Watson, X train, Y train, past the kernel. This initializes the model, and I'm going to go through a for loop. I apply the model to X test and H. The current bandwidth is H. It's the for loop, and I compare it with 1/2. So that's my eta hat. Right, so the regression I can compare it with hat type like this is like technical part. So you get y hat, like 0 1s. And then I compare with the y test, turning it to float, take the mean. This is a tensor of dimension, I take item with the number. So this gives me the test error. So average is classification error. And then append it to the test errors, which is like a computing. So I get a list of test errors for different edge. And here I'm going to plot them, right? So here you plot them, and so you can see that's how the plot looks like. And then there's this part where you can put it through the optimal. So the minimum argument, consider the argument, nullify argument, apply the test errors, and then that's the optimal value and plot it and print it. That's the optimal value. That's the optimal. Sounds good. Okay, and then your other time, so you can go through this other file, which is this does the Titanic with that mixed kernel, which with tensor product kernel. So you have like a discrete feature and a continuous feature. So here you just design. So there's this imputation because some of the data is missing. So here you impute by replacing A with the median. You can do it in different ways, but that's something that you have to figure out to do what to do. And this goes through the logic of how this kernel is calculated. So this is the kernel. So when you redefine your kernel, this does a different thing, but it's pretty easy to train and by n equals, and then there's zeros to the same. So the way that you do it is like you apply the Gaussian kernel to the A, and here you apply this is on the screen, it's like a fancy way of doing this pairwise comparison. So you play with this, the top code sphere out of this trait. But this is computing that kernel, like mixed kernel. And then you apply this is the kernel, and then you apply the same procedure, and then you get optimal bandwidth. Okay, sounds good.